Part A. Write 1 over 19 minus root 33 in the form p root 33 plus q, where p and q are fractions. This is a straightforward problem in rationalizing the denominator of a surd expression. So we multiply our original fraction by 19 plus root 33 over 19 plus root 33, which is 1. And so this operation does not change the value of the original fraction, it merely changes its form. Now we multiply the numerators and denominators of the two fractions, and we simplify the denominator according to the difference of two squares identity, which produces 19 plus root 33 over 19 squared minus root 33 squared. And if we don't have a calculator, we can evaluate 19 squared as 20 minus 1 times 20 minus 1, which foils out to 400 minus 40 plus 1, which is 361. And so we get 19 plus root 33 over 361 minus 33, which is 19 plus root 33 over 328. And splitting that up into the required form, we see that p equals 1 over 328, q equals 19 over 328. Part B. Hence show that root 19 minus root 33 is greater than 18 over 5. Since this is a hence question, we have to use the result from part A to prove it, and this in unsimplified form is the result from part A. Now the result from part A has no square roots on the left-hand side, whereas our inequality does. But we can remove the square root from the expression we have to demonstrate by squaring both sides. And that's quite safe because squaring preserves positive inequalities. So if b is greater than a and both b and a are greater than 0, then b squared is greater than a squared. The key point being that the direction of the inequality hasn't changed. So if we take the inequality in question and we square both sides, we see that if root 19 minus root 33 is greater than 18 over 5, then 19 minus root 33 is greater than 324 over 25. And we can note that 19 minus root 33 appears in the denominator of the result from part A. And we can also note that the 324 in the numerator of our new fraction is numerically quite close to the 328 in the denominator of the result from part A. And we further note that the 25 in the denominator is numerically quite similar to the 19 plus root 33 in the numerator of the same expression. Now, in the inequality that we have to prove, we need whole numbers, so we will have to replace root 33 with some suitable inequality involving only integers. And to do that, we note that 33 lies between the square numbers 25 and 36. And on taking square roots, we see that 5 is less than root 33 and root 33 is less than 6. However, we are really interested in the quantity 19 plus root 33, and we can obtain that by adding 19 to both sides of these inequalities to see that 19 plus root 33 lies between 24 and 25. And so we have two potentially useful inequalities for 19 plus root 33. And since we are trying to derive an inequality, we may as well write down the obvious inequality for the denominator. And we start with 324 is less than 328, which gives 1 over 328 is less than 1 over 324, which follows from the fact that if A is less than B, then 1 over B is less than 1 over A, as long as A and B are both greater than 0, which is the case here for 324 and 328. And now it's straightforward to derive the required result. we have that 1 over 19 minus root 33 equals 19 plus root 33 over 328, which is less than 25 over 328 due to this inequality, which is less than 25 over 324 due to this inequality, but that, as we have seen above, equals 5 squared over 18 squared. And so inverting the appropriate fractions, we have that 19 minus root 33 is greater than 18 squared over 5 squared, where we once again use this result. And on taking the positive square root of both sides, we have that root 19 minus root 33 is greater than 18 over 5, as required.